So, just to kind of recap what we've done since it's been a minute since we've been in class. So, say we have the matrix and I ask you guys, what is A21 equal? 1, right? So this is telling me the second row and first column. So that's not 1. It is 5. Oops. If I asked for the dimension of A, what would we say that is? 2 by 3. Remember, rows are always listed first. And the rows are the ones that go left and right. The columns go up and down. Okay. If I wanted to add these two matrices together, what am I going to get? Okay, and then what goes in this spot next? -2, and then, yep. Okay, good. What if I had asked you to subtract these two matrices? Good. So this answer does not exist, or you could say it's undefined. The reason being the dimensions of these two matrices are not identical. Matrices need to have the same dimension if you're going to add or subtract them. Okay? And we talked about scalar multiplication. What do I get when I do this? What's the first value here? Yep, and then the next one here. Okay, and then here. And then here. -4. Everybody feel okay with these kind of couple of basic matrix operations? Are there any restrictions on what I can scalar multiply with? Yeah, it's not like matrix addition, though, where the dimension has to be a certain way, right? I can do scalar multiplication with any matrix, right? Okay. So today, we're going to continue on, and now we're going to talk about a new operation called matrix multiplication. And most of today we're going to spend talking about matrix multiplication, as this is a much less intuitively defined operation than the previous ones. So we have to be a little bit careful here. So matrix multiplication, first things first, is defined only when the number of columns of matrix A is equal to the number of rows in matrix B. So can we multiply any two matrices together? No. The columns of the first matrix have to match up with the rows of the second matrix. Okay? Now, when we do that multiplication, the result, the product of that multiplication, we can predict the dimension of the answer. The answer's dimension is going to be the number of rows in the first matrix by the number of columns in the second matrix. So the entries in that product are found by multiplying each entry in each row of matrix A by each entry in each column of matrix B, and then taking the sum of those little multiplication problems. This is a little wordy. We're going to do some numeric examples in just a moment to kind of get us a little bit more comfortable with this process. And it hopefully will make a little bit more sense when we do that. Before I do that, though, I want to just kind of talk about the dimension here real quick. So matrix A times matrix B. If A is an n by m, and B is an m by r, can I do that multiplication? M, n, and r are just integers, like whole numbers. They're the dimensions. So yes, we can do this multiplication because the number of columns in matrix A is equal to the number of rows in matrix B, right? So what you're looking for is the middle part of the dimension to match up. Our answer, let's call that matrix C, is going to have what dimension? It's going to be n by r. Yeah.
So it's not an x, it's
Like if you were talking about pieces of lumber, you might talk about a 2x4, which is 2 inches by 4 inches.
Okay. Oh, yeah.
Like that board sitting there next to the file cabinet is a 2x4.
Okay, yeah. So then basically, if it both has the M
In the middle,
in the middle, then
and it works. If the same number in the middle. Okay. So the way that, or an analogy, or not a metaphor that we can use to remember this is multiplying matrices is kind of like falling in love. No, it's not that. Not that. It's that two people that look different on the outside but are the same on the inside end up falling in love. And when they have a child, that child looks a little bit like the first person and a little bit like the other person. Right? Very cute. Okay. So hopefully no one will remember, or no one will forget that, because they'll be like, oh, I'm just like falling in love. I think Mr. McCaskey, I stole that from him. But yeah, I think that's where I've heard that before. I didn't make it up. All right, so let's do a numeric example. Yes? And I'm going to do some color coding here to make this a little bit easier. I'm going to write one matrix in red and one matrix in blue, so it'll be a little bit easier to see where the numbers are coming from. So the first thing that I want to do is I want to check to make sure this multiplication problem is even possible. So I'm going to write down the dimensions real quick. What's the dimension for this first matrix? That's a 2 by 2. And what's the dimension for the second matrix? 2 by 3. Can I do this multiplication? Yes. Because the 2's are the same. Okay? So what will the answer look like? What's the dimension for the answer going to be? 2 by 3. So I'm going to write a little spot for each of these answers. Okay. And I'm going to put my work in each of these little spots. So this is not like I'm not trying to create a fraction right now. I'm just creating a blank to put each one of my answers, because I know I'm going to have like 6 entries inside of this. Remember that we called this first entry like entry 1, 1 because it's in the first row in the first column. This is 1, 2. This is 1, 3. This is 2, 1, 2, 2, and 2, 3. Everybody's okay with that? So to get the entry 1, 1, yes, go ahead. To get this first entry 1, 1, I'm going to multiply the first row by the first column. Notice first row, first column. That's where that answer is going to go. So I'm going to do negative 2 times positive 3. And then I'm going to do positive 3 times negative 1. And I'm going to add those two numbers together. So I'm going to multiply the corresponding elements in the row of A, in the column of B, and then add those things up. And I'm going to do that for each of these 5. So the next piece is 1 and 2. So I'm using the first row still, but now I'm using the second column. So I'm going to do negative 2 times 4 and positive 3 times 0 and add those up. Everybody okay so far still? Okay. The next piece, I want row 1 with column 3. So I'm going to take row 1 and multiply it to column 3. So I'm going to have negative 2 times positive 5, and then positive 3 times positive 6, and then I'm going to add those up. Now I've multiplied row 1 with each of the 3 columns. So now I'm going to move down to row 2 and multiply row 2 by each of the first 3 columns. So now I'm going to use the 4 and the 5. So I have 4 times 3, and then 5 times negative 1, and I'm going to add those 2 up. And then I'm going to do row 2 and column 2. So row 2 and column 2. I'm going to do 4 times 4, and then 5 times 0, and add those up. And then the last spot, we're going to do row 2 with column 3. So this row 2 times column 3. And have positive 4 times positive 5, and then positive 5 times positive 6, and add those up. On the test or quiz, I would expect to see this step written out, where I can see that you're multiplying things correctly together. I would not need to see any more intermediate steps other than this, but I would need to see this step in between our final answer. Just to pause here for a moment, and if we look at this intermediate step, what patterns do you guys see? Look at the red numbers in row 1. They're all the same red numbers in row 1, right? Look at the red numbers in row 2. They're all the same. Look at the blue numbers in column 1. They're the same. And the blue numbers in column 2, and the blue numbers in column 3. So that's a nice little check that you can do before you go move on to make sure that you've gotten everything in the right place. Is everything should line up really nicely and neatly. And if you want to do multiple colors when you do your assignment, that's perfectly fine until you get the hang of kind of what's going on. That can certainly be helpful. Okay. And so now to finish this out, we're just going to go ahead and do these multiplications. So negative 2 times 3 is negative 6, and 3 times negative 1 is negative 3. Negative 2 times 4 is negative 8. 3 times 0 is 0. Negative 2 times 5 is negative 10. 3 times 6 is 18. 4 times 3 is 12. 5 times negative 1 is negative 5. 4 times 4 is 16. 5 times 0 is 0. 4 times 5 is 20. And 5 times 6 is 30. So my final answer then would be negative 9, negative 8, positive 8, negative 7, 16, 50. Yes, Clayton? Sure. What do we think there? Not so bad? Again, like this is definitely more involved than the previous 2 operations, right? Definitely this is not what you would have expected if I was asking you to multiply 2 matrices together. This procedure is not the obvious result. But in doing the process, I mean, it's not so bad. It's a little bit of writing. but you're just doing multiplying and adding numbers. It's not so bad. Just remembering the order to do it. Let's do another one, just to make sure we've got it. So I'll color code this again for us, and we'll do another color coded. Eventually we're going to stop color coding these, just FYI. But here in the beginning, I see no reason not to do that. Oops. What was the other color I've been using? I used blue, right? So what's the first thing we should check? Yeah, we should check the dimension to make sure the multiplication is possible. What's the dimension for the first matrix? 2 by 3. And what's the dimension of the second matrix? 3 by 2. So is this, it does work. And what will the answer look like? It'll be a 2 by 2. The outsides. So I'm going to write out a little kind of place to put my work in. Everybody's okay with that? Okay. So I'm going to take the first row and then multiply it to the first column. Oh, I can color code this better. It's really yellow is doing that. And we'll do the second or the first row with the second column. So far, so good. Then we'll move on and do the second row, again with the first column. And then lastly, I'll do the second row with the second column. Everybody so far so good? Now all I have to do is do these little multiplication problems and then add up my results. Let's see, I have 30. Okay, so for example, if I look at this first entry, I'm using row 1 with column 1. So I have row 1. So I'm going to multiply the first entry in row 1 with the first entry in column 1. then the second entry with the second entry, and the third entry with the third entry. That's it.
Yeah, not that part, but then we're gonna get to the other ones on the
Okay, so maybe we want to talk about this one here. Okay, so I'm going to be using row 2 with column 1. So again, I'm going to multiply the first with the first, the second with the second, and the third with the third. So it's always the corresponding spots. That's why the columns and rows, that middle dimension matters. Because if I don't have the same number of rows and columns, or columns and rows there, I wouldn't have things to pair up together. All right, so we have 35 plus 3 plus 40, and then I have 10 plus 0 plus 4, and I have 0 plus negative 9 plus 60, and then 0 plus 0 plus 6. So my final answers are going to be 78, 14, 51, and 6. Everybody okay with how we got those? Okay. Now it's time to start investigating some properties. So the first question I'm going to ask is matrix multiplication commutative. And what do we mean by commutative? We mean A times B is equal to B times A. A and B are matrices. Because we're talking about matrix multiplication. Is that going to be true? No. Why not, Jack? What do you mean not the same? Okay. Yes. Let's think about this real quick. Can I multiply these two together? Yes, right? What if I switch the order? Can I multiply those together? No. So right there is an excellent reason why matrix multiplication is not commutative, right? Because right away, if I multiply two matrices together, it might not even be possible to switch their order, right? Let's say, for example, the matrix, let's say it is possible to switch their order and it works both ways. Could these be commutative? No, why not? What's this first matrix going to give me? It's going to give me a 3 by 3. What's the second one going to give me? 2 by 2. Everybody okay with that idea? So even if I can switch the order of doing the multiplication and get an answer, we're not even guaranteed to get the same size answer. Right?
So you want 3 times 3 times, like for both?
What? I'm sorry. What are you asking?
So you want the 3 by 3 or the 2 by 2 like both, like 1 times?
We would want the same two matrices.
Really both.
So what we're saying, Sierra, is for two matrices to be equal, at minimum they need to have the same dimension, right? If they don't have the same dimension, they cannot possibly be equal. We're trying to tell if A times B can equal B times A, right? So we've seen in general that's not going to be the case because it might not even be possible to multiply the matrices in either order, right? We're seeing a second case now. What if we can multiply them in either order? Well, we're not even guaranteed to get the same dimension with our answer, in which case they couldn't be equal. If we're searching for a time where they can, what if I have a situation like this? Are these going to give me the same answer? Well, the answer is going to have the same dimension, but will the matrices in general be the same? Let's check. Let's just do a numeric example to kind of check, right? Sound okay? So we'll just do a little 2x2 guy here. I do that, I get 3 times 5 plus negative 2 times 1, and I get 3 times 0 plus negative 2 times 6, and I get 1 times 5 plus 0 times 1, and then 1 times 0 plus 0 times 6, and that simplifies down to 13, negative 12, 5, and then 6. Okay. Now let's switch the order and see if we get the same answer. 6 times, oh, thank you. So if we do this now, 5 times 3 plus 0 times 1, and already I'm done, right? Because what do you notice about the first entry? It's different. So are these two matrices going to be the same? No. So that's the question then. So in general, yes, we've established. Stop talking, please. So in general, with our first example, we found one counterexample immediately to say that this doesn't work generally, right? What we're doing now is we're looking for, does it ever work? So we've seen that even if we can multiply both directions, we're not guaranteed to get the same answer, okay? If we multiply two square matrices together, we're guaranteed to get the right dimension, but right away with our first counterexample, we see that it doesn't work for any two square matrices. The question we're left with then is the question, are there any square matrices that commute? The answer here is yes. So let's try to think about some situations where this might work. We've seen that we have to be pretty careful because just picking two random square matrices like we did before, it did not work. What's an example of when it might? If they're all the same number, can you describe to me what you're saying? So if we're doing just two 2x2 matrices, what's in the first matrix? Okay, and what's in the second matrix? You're just saying that. So A times A is definitely going to commute, right? If I have the same matrix, even if they're not all 2's inside of it, if it's the same matrix, it's going to commute, right? Everybody's okay with that idea? So this is an example. A times A is obviously equal A times A, right? Okay. So that's one situation where it'll work. Can somebody think of another one? There's another kind of obvious one that I'd hope we could come up with. Marshall? Great. So we had a special name for that. We gave it the zero matrix name. And we used the letter O to represent that matrix. But yeah, that one will commute. So if everything in one of the two matrices is zeros, that will commute with, doesn't matter what A looks like, what the entries are, they're just, the dimensions have to match. That's good. That was the other one that I'd hope we'd come up with. There are two more important situations where this does work, and we're going to come back to those in a moment. Okay, because it's probably too much to catch those right now. But we'll come back there in a minute. So the next question I'm going to ask is, what is the multiplicative identity for matrix multiplication? So when we say multiplicative identity, I want to know what matrix can I multiply by A to give me A. Conversely, since we know that matrix multiplication is not necessarily commutative, right now we've only seen that it's commutative in like two very specific situations. This multiplicative identity needs to be one of those numbers, or one of those matrices that does commute. So we need to figure out a matrix question mark where that's going to work. Anybody with any idea of what that might be? What that might look like? Well, let's start with like a specific example. Okay, you want to try all by ones. Good. That's a natural first guess. Okay? So let's go ahead and see what we get when we do the multiplication. So I'm going to get 3 times 1 plus 1 times 1, and already I get 4. Well, is that going to give me matrix A? Well, A is... Okay, so Jack says, let's make this next one, or I'm sorry, it's not that one. You said wanted this one to be 0. Right? Okay, so if I do that, this becomes a 0, and we get 3 here. So that's good. So far, so good. Let's keep going then. Then we're going to do row 1 times column 2. So it's going to give me 3 times 1 plus 1 times 1, which again gives me 4. That's not what I want. What should this one be? Needs to be a 1. So what should I change in matrix question mark? Yeah, which one of these two ones needs to be a 0? This first one, right? Where did that correspond? Was that one there in the matrix question mark? Well, we didn't have any intuition. We're going to figure this out, and then we're going to generalize this to be able to predict what this will look like in general. But right now, we didn't have any idea. We just know what it needs to do, and we're just kind of figuring it out what it has to look like to do what it's supposed to do, if that makes any sense. So this is kind of like a little ad hoc. Yeah, it means like, like by the seat of your pants. We're just kind of figuring it out on the fly. Okay. So if I do the next thing, I'm going to get 0 times 1 plus 5 times 0. Well, that gives me 0. That's good. And we'll get 5 times 1 plus, 0 times 1. 0 times 0 plus 5 times 1, which is 5, which is also what we want. So we've got it perspectively. So we think that for 2 by 2s, this is our identity matrix. 1, 0, 0, 1. But we still have another direction to check. We still have to make sure that if I go the reverse order, that it works. Let's check that real quick. Guess what? It does. Cool. So we found the 2 by 2 identity element. What do we think the 1 by 1 identity element is going to look like? Hopefully nobody has a hard time seeing that's going to be 1. What do you think the 3 by 3 identity element is going to look like? Yep, so it's going to have 3 rows and 3 columns. What's going to be in the first row? One, 0. What's the second row going to be? What's the third row going to be? Do we see the pattern now forming? So we just have 1s down the main diagonal from left to right and 0s everywhere else. So the notation we're going to give this matrix a special name. Guess which letter of the alphabet we're going to use? We're going to use I. Why do you suppose we picked I? It looks like the number 1. And what is this behaving like? The number 1 when we multiply real numbers. So we can say like I 3 by 3, I 2 by 2, I 1 by 1, etc. Everybody okay there? Okay. So we can go back and add this to our list. Of things that do commute. It's a small list. There's going to be one more that we need to talk about. So the first thing we want to do is talk about what does multiplicative inverse mean. So by multiplicative inverse, I want two matrices. When I multiply them together, I get the identity element. So let's try to do the same kind of thing from a, just like on the fly figuring it out perspective. So I've just written a random matrix here, A. We're trying to figure out what question mark is to get us the identity matrix. So when I multiply the first row by the first column, I have to get 1, right? So 4 times, I'm going to call this question mark 1, 1, plus 1 times question mark 2, 1 has to give me 1, right? Okay. If I do the same thing, then I can say 4 times question mark 1, 2 plus 1 times question mark 2, 2 has to give me 0. And then 11 times question mark 1, 1 plus 3 times question mark 2, 1 has to give me 0. And then I have that 11 times question mark 1, 2 plus 3 times question mark 2, 2 has to give me 1. What do you guys see here? Notice those are two variable systems of equations, right? The variables in each of those that I've highlighted are the same. Question mark sub 1, 1, question mark sub 2, 1, question mark sub 1, 2, question mark sub 2, 2. And we know how to do that, right? So what are those going to be? That's what it comes down to. I skipped solving the system because I know how to find the answer without having to solve the system. But it does work. Sometimes. Because what's possible when we solve a system of equations? Are you always guaranteed to get an answer? No, right? You could get no solution or infinitely many solutions, right? Either of those are going to be a problem. So in those cases, those matrices don't have multiplicative inverses. But this is not going to be the way that we're going to use to find these multiplicative inverses. This is a harder way than it needs to. but I wanted to give you a feel for like what you would try to do just intuitively, right? We did nothing fancy here. We just kind of thought about what we needed to have happen with a numeric example. So first things first, we need to define a new matrix operation. So I'm going to take an aside here because we need this new matrix operation in order to finish our description of what these inverses are going to look like. This new matrix operation is called the determinant. The determinant of a matrix is only defined for square matrices. Since these are the only matrices we can take the inverse of, because we need to end up with the identity matrix at the end, which is always a square matrix. So we can only do it for square matrices. So for a 2 by 2 matrix, the determinant of the matrix A, B, C, D is equal to A times D minus B times C. What did we do there? We took the main diagonal minus the other diagonal. Also worth pointing out, there's an alternate notation for determinants other than writing DET. If I write these straight bars that aren't the brackets, that means the same thing as taking the determinant of the matrix. Okay, so you'll see that in the homework as well, that notation used. It's probably the more common notation than writing DET of the matrix. Don't be confused, it's not an absolute value. It's a different notation. Okay? For 3 by 3s, it's a little bit more complicated. So what I'm going to show you guys is called the diagonals method to do this, and it's a very visual method. So this is the matrix that I'm going to take the determinant of. The first thing I'm going to do, and this is just so I can figure out the formula, is to recopy the first 2 columns of this matrix on the right side of the matrix. So I'm going to copy the column ADG and the column BEH. I'm just recopying this, and it's just so I can figure out the formula. Because this is a process, this is a situation where you don't want to try to memorize the formula. You want to memorize the process and how to find the formula, because the formula is like an alphabet soup of confusion. But the process of how we get it is very visual and much easier to remember. Okay? So what we're going to do is we're going to multiply these 3 downward diagonals together and then add them up. And then we're going to subtract from that the product of these 3 upward diagonals. And that's how we can compute the determinant for a 3 by 3. Now, you tell me, which would you rather memorize? This process or that formula? The process, man. I don't want to memorize that formula. Goodness gracious. There's no way I would remember that. I'm going to remember that process, which is very easy. It's visual. I'm just like, oh, we copy 2 columns, those 3 diagonals minus those 3 diagonals. Easy. Much easier than like, okay, it was E times I, like the letters, it's just a mess. All right, let's do a couple quick examples of finding the determinants. So this is a 2 by 2 matrix, right? How do I compute this determinant? 3 times 6 minus 5 times 7. So negative 17. That's not so bad. So let's compute the determinant of this 3 by 3 matrix. What's up? No, what's up?
No, I was just thinking of
Oh. Okay. So the first thing we do is recopy the first 2 columns. And I'm going to write those always on the right-hand side. And then I'm going to multiply the 3 downward diagonals together. And then add up those answers. So 1 times 6 times 0 plus negative 1 times 1 times negative 2 plus 0 times 3 times 3. And then I'm going to subtract from those the 3 upward diagonals. So then I'm going to have, and this is really should be one line, I've just run out of space, minus negative 2 times 6 times 0 minus 3 times 1 times 1 minus 0 times 3 times negative 1. And when I do this multiplication, I get 0 plus 2 plus 0 minus 0 minus 3 minus 0. So this determinant comes out to be negative 1. We okay with that one? Okay. So that's going to end our little aside. And I have just only enough time to write down the formula for a 2 by 2 inverse. So when we come back, so for A being the 2 by 2 matrix A, B, C, D, A inverse equals 1 over the determinant of A times the matrix D, negative B, negative C, A. over the determinant of A, det of A. So in this case, what's the determinant of A going to be? Just AD minus BC, right? When would the inverse not exist then? When AD minus BC is equal to 0. Why would that give me a problem? I'd have 1 over 0, right? That's undefined. That's bad news, Charlie Brown. All right, we'll finish here for today. I don't need you guys.